Hello everyone. So welcome to my new episode. In this episode we are going to talk about marginal rate of substitution, and let's start with our utility framework. Alright, so instead of speaking a more abstract set of alternatives, we are going to make it more concrete. So our set of alternatives are going to be coming from the vector space Rn. And usually for simplicity, we may assume n is equal to 2, but all our arguments will be actually true for any n greater than or equal to 1. All right, so remember we started with a set of alternatives x, and so for most of our lectures, we are actually concentrate on r to the power n, where n is greater than or equal to 2. When n is equal to 1, well, it's not really an interesting choice problem, all right? And so on top of that, we are going to put this plus sign there because we do not want negative numbers entering into our consideration. And here the interpretation is the following. An alternative is in fact, so let's call this alternative x. So it's x1, x2, all the way up to xn. And or if we're talking about an alternative y, it's y1 all the way up to yn. All right, so they are vectors in Rn plus. And that means xi and yi from 1 to n, they all are either 0 or a positive number. They're never negative. So that basically means our alternatives, the interpretation is that the alternatives are what we call consumption bundles. All right? Consumption bundles. So each x and y are called bundles or baskets, all right? And so we call them consumption bundles. The idea is that there are n different goods, all right? And then the consumer or the decision maker would like to buy either 0 or some positive units of each good, all right? So you can obviously skip some goods and you can buy positive amount of others, but you can never get negative, all right? That's a simplification assumption. Obviously, we can extend our arguments to the environment where the x's can be negative, but let's stick to this environment first. So the idea is like you go to a grocery store, all right, and you want to cook dinner, and you're planning of making a pasta. And so what you need is, well, pasta, and then probably tomato sauce, and then maybe some Parmesan cheese, and all the other ingredients that you want to add, and you think that they're not available at your home. And so there are n different goods, and the question is, how much to buy each kind of question. All right, so that's the interpretation. All right, so the simplest environment is obviously when n is equal to 2. It's simplest because we can visualize everything like the utility functions, indifference curves, and everything when n is equal to 2. So in this environment, for instance, r to the power 2 plus is basically the first quadrant of the r square environment. So this is the first axis. We usually denote it by x1, and the second axis we usually denote it by x2, or if we're talking about y, this is y1, y2. All right, so this is the first coordinate, second coordinate, and obviously this is the 0, 0 point. All right, so our consumption bundles are here. Well, clearly, infinite amount of goods is not feasible in almost any setup. So then you may wonder, why do we really care about sort of infinity? I mean, why is this set not bounded? Well, I mean, actually it will be bounded by, for example, the budget constraint, right? I mean, if you want to buy a certain amount of goods, well, the thing is you have to pay for these goods, and nothing is free, and so therefore the income or your wealth is going to be your constraint. So there is going to be some bound imposed on this question or in this setup. But for now, let's leave the mother set of alternatives as free as possible. All right. So the only restriction I impose is that nothing can be negative. All right, so in this framework, a utility of an alternative x is in fact the utility you derive from every single good you consume, right? That's the idea. All right, very well. Well, because all these xi's are real numbers, right? By the way, don't forget, so the xi for every I is a real number, right? So x1 is a real number, x2 is a real number. So therefore a vector x1, x2 is a vector from our square. All right, so the utility function is going to map each vector to a real number, like for example, consuming 5 units of tomatoes, 2 units of apples, and 3 units of banana, while my utility out of this is 10 units, all right? Whatever the unit is. It's not kilo, it's not pound, it's not dollars, it's just some unit, remember? So the utility always assigns a real value for every alternative available. All right, so because there are infinitely many availables, remember x's are coming from Rn, because there are infinitely many alternatives. If you remember our previous discussions, a preference relation, which is a binary relation that is complete, transitive, and reflexive, can be represented by a utility function. Well, we had the theorem, if the preference relation is continuous, all right, in this huge domain, well, then we can actually find a continuous utility function. So most of the times, we are going to sort of leave this abstraction of preference aside. We don't really need it. We are actually going to work with the utility functions for the rest of it. Well, why is that? Well, because the utility functions are nice, because I can it gives me a way of measuring the comparisons between the alternatives. All right, so this measurement, I am going to define new concepts like marginal utility, marginal rate of substitution, and so on. But one final thing that you shouldn't forget is that if U is representing a preference relation, remember some increasing function f of u will also represent the preference relation. All right, so this is what we call monotonic transformation. Monotonic transformation. So where f is again a strictly increasing function from reals to reals. All right, while why it is from reals to reals but not from Rn to reals, well, the answer is simple, because the inside of the brackets f of, so the domain of f is actually utility value of each, all right, so f of u of x. All right, so the domain of utility function is a vector, so u is defined from Rn to R. However, f's domain, it takes values from u of x, utility value of x, and the utility value of a vector x is just a real number, 5, 7, 3.5. All right, so therefore f is a function which maps reals to reals, not Rn's to R. All right, so be careful about such sort of simple technical details so that they don't confuse you later. All right, so where are we? Okay, so we talked about the setup, the formal setup. So in this setup, we can define marginal utility as follows. Marginal utility. So what is marginal utility? It is basically a change in utility per unit consumption. All right? So first, what is consumption? Well, consumption is sort of increasing the amount of, so if your utility function is x, and let's suppose x is not a vector, it's just, one variable, one-dimensional variable, all right? So increasing or decreasing x is basically increasing your consumption, decreasing your consumption, all right? So that's the lingo. All right, well, given this, marginal utility means the change in the utility level, all right? You get happier or sort of worse off. So change in utility level per unit consumption. All right, so for each unit consumption, meaning as you increase x, your consumption by 1 unit, how much utility you're going to, how much additional utility you're going to get. That might be positive, that might be negative. So if it is positive, that means you're getting happier. If it is negative, that means you're getting worse off. All right? So, well, why do we call it per unit consumption? Well, because the unit of the X depends on the setup, right? If, for example, X, the alternative, is a discrete variable, for example, it is a number of apples you buy, all right? You can't buy half an apple from a grocery store, all right? So if this is the case, if X is a discrete parameter, all right, or, hiring somebody new, so you can't really hire someone, half a person. So if X is a discrete variable, well then per unit consumption basically means what's going to happen to my utility if I consume by, I'm going to distinct consumption and buying in a moment, but let's leave this aside for a moment. So if I consume 1 unit of apple, how much utility, additional utility I'm going to get, all right? That's the idea of marginal utility. Well, if X is, however, not a discrete variable, but it's a continuous variable, meaning you can divide X as many times as you like. I mean, to be honest, there is no perfectly divisible good, real good. Well, maybe air, maybe water. I mean, even them, I don't think they are perfectly divisible because the smallest element of water is kind of discrete. Anyway, put that aside. So the continuity of a variable is just an approximation just for simplicity, because a discrete environment is really hard to work with because you cannot really use the optimization theorems like Kuntaker, Lagrangian, etc., etc. So this is why we just, for technical reasons, assume continuity. But if you can divide X for any infinitesimal amount, all right? Well, then the per unit consumption then means what? Well, so it's basically the marginal utility in this framework is nothing but the utility, the derivative of the utility with respect to your variable X. Here I didn't use del U del X because I assumed the X is a real number. So this is a utility function with one parameter only. Sorry. But if we are talking about, for instance, xy, all right, so here x is a real number, non-negative y is a real number, a non-negative real number, all right, so this is basically R2. Again, as you see, I am interchanging the notation. So sometimes I denote x as a vector itself, like n-dimensional vector, and same for y. But some other times I denote x and y's as real numbers. All right, so be flexible about sort of playing with the notation. So be careful about all these. All right, so x is a real number, y is a real number. So therefore, my utility is defined over r squared plus. All right, so if this is the case, meaning I consume two different goods, apples and bananas, well, then I can talk about my marginal utility with respect to apples and with respect to bananas. All right, so this is the percentage change in the value of the function with respect to the per unit change in the variable. Actually, it's a standard definition in mathematics. This is simply nothing but the slope of the function with respect to the one variable. All right, so the marginal utility is nothing but a percentage change, a change in the function per unit change in the parameter. All right. So one point that I wanted to make is like consumption versus buying. So utility is normally, we assume, is what you feel once you consume this good. All right. So when we talk about a utility of some vector or real number, doesn't matter, x alternative, this is the utility you're going to get once you consume this x. All right, so buying something may not give utility or may give utility. I mean, to be honest, buying And for example, buying clothes and not wearing them at all sometimes gives people, I mean, it may give utility to people. So here, I mean, technically, I don't know how to differentiate these two environments, but just to be clear, is that we are not talking about utility out of buying something, but we're talking about utility out of consuming something, all right? So your preferences are about consuming something, not just buying it, all right? So I hope I did not make it even more complicated. All right, so this is what marginal utility means. All right, what about marginal rate of substitution? Well, marginal rate of substitution is going to kick in when we have more than one variable, obviously. All right, so we need to have a situation like this one. So the alternatives must be vectors. So there should be at least two different goods you're consuming. So because rate of substitution. So the question is, if I want to give up some of my consumption, some consumption from one good, how much additional consumption I need to make on the other good so that my level of utility is the same. All right. So remember here, my level of utility basically means my preferences, my indifference level is the same. So here I am trying to keep myself indifferent between two situations. Situation 1 and situation 2, these situations differ how much I consume in each good. All right, so that's the definition of or description of a situation. So in situation 1 and in situation 2, I would like to be indifferent. All right, I would pick either this one or that one. Nothing is going to hurt me or make me happier. So the question is, what is the difference between these two situations? Well, the difference is that I give up some consumption in one good one. All right, and then here. So given that I am consuming, 5 apples, 5 bananas, here I am decreasing my apple consumption by 1 unit, let's say. So instead of 5 and 5, I consume 4 apples. The question is, if I consume, maybe I should write it. So the situation 1, I have 5 and 5 apples and bananas. Situation 2, I consume 4 apples. All right. Well, if in the situation 1, if I'm consuming 5 and 5 apples, 5 bananas, and if I'm already consuming less apples, if I keep my banana consumption same, meaning 5, well, this will most likely decrease my consumption. Here we have a sort of implicit assumption. All right. We assume that, we didn't really mention about it before, but we assume again for technical reasons, just for simplification, because it's almost always easier to work with monotonic function, meaning, increasing or decreasing. So the fluctuation functions are complicated. So for simplicity, we usually assume increasing utility function, meaning the more you consume, the happier you're going to get. All right, that's the implicit assumption that we have, and we're going to stick to this unless I tell the otherwise. So therefore, the 4-5 is definitely less than 5-5, right? Because the first component is less, although the second component is the same. So if the utility function is an increasing function, that means you're going to get worse off in this second situation. So remember, the idea was to keep my level of happiness the same. So therefore, if I want to decline my consumption on apple, I have to increase the consumption of bananas. So 5 plus some epsilon. So epsilon is some positive number, clearly. So how much additional banana I should consume so that I am indifferent between these two bundles. So the amount of this apple is going to basically give me the marginal rate of substitution. Well, it's not marginal, but it's going to give me the rate of substitution. All right. So for 1 apple, I need to consume epsilon additional banana. So that is the rate of substitution. So if epsilon is equal to 2, it's 1 to 2. So if I give up 1 apple, I need 2 additional bananas. All right. The marginal comes from, if I make these changes instead of from 5 to 4, but it's 5 minus Okay, sorry. That was my clock. So instead of 5, instead of declining my consumption from 5 to 4, let's make it 5 minus delta, all right? So delta is some positive number. So then the question is how much additional banana, epsilon, could be very, very small. So this is per unit of change, all right? So again, if these are discrete goods, well, then that's going to be, delta is going to be 1, 2, 3, and so on. But if it is not discrete, well, then it's going to be d of x, all right? And so this is going to be d of y. So if this is good x, if this is good y, all right? So something like this. So that's sort of the intuition behind the rate of substitution and marginal rate of substitution. So how do we calculate the marginal rate of substitution? And this is what I will explain next.